So this is where we are. Yeah. Did anyone do their homework assignment last night, by the way? No. No. Come on. Oh, I better check my voice. Oh, okay. So that's fine. It's there. Should you ever want to do it, I guess is the deal. You see from this exactly where we are and where we're going. We spent our time talking about flow equations, from understanding what the conservation equations are, the governing equations are, simple one-dimensional models and two-dimensional models for triangular elements, more sophisticated ways, which are the industry standard for isoparametric elements, such as are used in COMSOL. How we take a steady state behavior and look at the transient behavior, which is really the essence of looking at flow problems by understanding what the mass matrices are and what integration in time is. We haven't covered either mass transport or Navier-Stokes equations. The Navier-Stokes equations, of course, are ones that include flow, but include also the inertial terms. And usually the difference between Navier-Stokes equations for fluids and creeping flow, if you like, in porous media, is that we assume in porous media that the viscosity of the media is included in this term for the permeability. The effects of permeability is the frictional drag, the viscous losses within the system. In Navier-Stokes equations, we solve a much more complicated set of equations, 4 equations instead of a single equation, 4 governing equations rather than a single governing equation as we do for porous media flow. And so it's important to use this if you have really high velocity flows or if you don't have a permeable structure that's restraining it. But for our characteristics, using permeability that really takes care of this frictional losses within the system is a much easier and certainly adequate way for us to look at flow behavior. The reason for including the Navier-Stokes equations in this class, if we had time to look at them, is that what we have dealt with so far, the conservation equation has just been a conservation of mass equation. Mass in, mass rate in equals mass rate out, which gives us a continuity equation. And then what we did with that was we inserted Darcy's law, if you remember. So Darcy's law is actually the way of being able to include both the inertial and the frictional drag effects that you'd see in Navier-Stokes equations. And so when we deal with porous media flows, the way that we deal with it is a different way than dealing with it in this way. It's perfectly adequate. But the Navier-Stokes equations are actually full momentum balance equations. And so since we have three-dimensional flows, we basically solve F equals ma, Newton's second law, in x, y, and z in the 3 directions. And then we have another equation that constrains them, which says that mass rate in equals mass rate out. In other words, we solve 4 equations. One is a continuity equation, which we defined here, same one, but also 3 equations for F equals ma in the x direction, F equals ma in the y direction, and F equals ma in the z direction, and then solve them. And so that is where we solve for momentum. And so the reason for putting it here is that now that we're going to talk about solid mechanics, solid mechanics is something where we're also solving for momentum. And so we could frame the solid mechanics equations in terms of F equals ma, and we could solve them for this dynamic behavior. But typically we don't, because we're not so interested in the dynamic part, at least not in terms of the inertial forces that are present. So if you imagine taking a building during an earthquake, inertia is a very important part of that, because it controls how it flops back and forth. And to be able to solve that, we need to be able to solve full dynamic system of equations, which actually would be very similar for fluids as it is for solid mechanics. The only difference between those two systems is that in fluids, the the constitutive law that we use is actually Newton's law of viscosity. Tau equals mu dV dx. I guess I write it on my page, so that shear stress is equal to mu times dV dx. And in solid mechanics, we use the model that stress, you'll see, is equal to the constitutive model times the strain. And this strain, of course, is equal to a change in displacement with x the same as this. And so when we look at these expressions, the similarity which we have in them, actually, which we have talked about, which is perhaps worth looking at, is that all that's different between Navier-Stokes equations and the deformation equations that we deal with for solid mechanics is that they have different constitutive relationships in them. And we've looked at this figure before. I want to bring it up again. I think we've looked at it before. No, not there. It's one of the figures which is horizontal in this. Not that, although that's interesting. I'm giving. Momentum transport is after that. Yeah, I'm not going to talk about Navier-Stokes, but I think this is useful. Yeah, this one. Okay. So I will use that. So you've seen this slide before, and so not included as one of the columns on here is the Navier-Stokes equation. But when we look at this, we made the point that the only difference between this is that the continuity equation that we have, we insert a constitutive equation. For flow, it's been Darcy's law. It could be Fick's law if we look at transport. In the systems that we look at, if it's Navier-Stokes flow, then the constitutive relationship that we put in is the one which is shear stress is equal to viscosity times the rate of change of displacement or velocity with location. And if we look at solid mechanics flow, this term du dx is actually displacement. This is strain, which is displacement rate. And in the case of this is velocity. This is a velocity rate in space. And so it's useful to think about it that way because it kind of contextualizes this. Because now, in all of these systems, the reason that we can solve them quite easily using finite element methods is that they all look very similar to each other. Conservation of mass in equals mass out, plus which is equal, and if they don't balance, it's equal to accumulation. A constitutive relationship, which is Darcy's law, which takes care of frictional losses, and then we apply boundary conditions to it. In solid mechanics, the conservation equation is a force balance. It's actually the equilibrium equations, which in our work we'll actually do by looking at the concept of virtual internal and external work. It's just an easier way to develop the equations. So this is a conservation momentum equation, but typically we're not interested in momentum, we're interested in just in forces, which are simpler because we're looking at static problems. And the constitutive relationships we apply are for Navier-Stokes flow is Newton's law of viscosity. Which says the shear stresses that you apply on a unit element of fluid relative to the velocity. This is the velocity versus the distance in the x direction. These are the terms here. So this would be the velocity. This would be the gradient of velocity as it goes across the sample to where it's anchored at the bed. Defines how big a shear stress you have to apply. Double the shear stress, you double the velocity gradient. Or if you change the viscosity, you change that as well.
In solid mechanics, it says that the larger the stress you apply, the larger the strain. So the strain is a displacement with location. This is a velocity with location. And so the difference between fluid mechanics and solid mechanics is really just the fact that we substitute a different constitutive relationship into the behavior, and then the equations actually turn out to be rather similar in many respects. So that was kind of trying to set the stage. So the dynamic part of porous media flows is not the fact that we deal with inertia, like in a building that's flapping backwards and forwards. It's the inertia of the building that controls the period at which that goes compared to the excitation on the base. But the control typically in these pseudo-dynamic systems that we have for deformation is that fluid pressures change with time. Those are the rate-limiting components. And as fluid pressures change, they change the magnitudes of effective stresses, and therefore deformations develop in accordance to those fluid pressure changes. And so typically we deal with static, non-dynamic mechanical behavior and link it with dynamic fluid behavior where the fluid pressures are evolving as a function of time. And so that's what we're going to attempt to do now. So I jumped ahead of where we are. So what we're going to talk about, I think, is in terms of solid mechanics. We need to develop the equations that govern behavior for deformation. And we'll try and do it for one-dimensional elements and two-dimensional elements, triangular elements, as has been our practice in the past. It's useful also to return to this figure. We haven't really come back to this figure very much, but we made the case for this figure the first time we met, the first time we were talking about this. If we're looking at deformations in the system, then the nodal variables that we'll apply will be for deformations. This is actually a velocity, a deformation rate of the nodes. And we link that to what's referred to as a stiffness matrix. And they're linked to a stiffness matrix by a force vector. So typically the expression that we'll end up solving looks very similar to what we've dealt with before. Instead of Q equal to KH, right? We've seen that equation many times. It's just a linear system of equations, A times X equals B. And the other interesting thing that we'll find out is that the stiffness relationship, which links the nodal stress displacements to the nodal forces, actually turns out to be something very similar to what we've seen before. You certainly will recognize this relationship. Always positive, definite, and well-behaved. But now the relationships which define the A matrix are now a little different. Now it links strains with displacements. And the constitutive matrix is Hooke's law. So this is Hooke's law. Where before it was Darcy's law. So before it was V is equal to hydraulic conductivity times dH dx. But it's actually quite similar. This is a strain, but a strain, if we write it out in shorthand, is a change in displacement with location, as indeed this is a change in head as a function of location. So they're related to gradients of these properties. And so there is some commonality in this. And so you remember before, what did we have? We had, this was, I think we called this R22. We called this S22. And we ended up with, these were our flow equations. This is our conductance matrix. This is our storage matrix, which operate not on pressures, but on heads, because we chose to write it in those terms. But it's basically the same thing. And so maybe this puts it in the right context for you. I won't say anything about this because we already know what finite elements look like, but other than to say that somewhere in your notes you'll also see some material that talks about boundary solution procedures, such as boundary element methods or boundary integral equation methods versus what I would call domain methods. So domain methods are things like finite difference methods or finite element methods, which are the top ones, finite difference methods, which are the bottom ones, typically on a much more regular grid, and finite element methods on an unstructured grid. But both of these methods here have the same outcome in that they completely fill the volume of the domain that you're interested in to define. Boundary element methods, B is for boundary element methods, have the characteristic that you only actually put elements on the boundary. So these are nodes on the boundary. This would be an individual element which is on the boundary, which would just be something that links two nodes, a bit like our one-dimensional element. And so the idea is that in some cases, especially some geological cases, where you're only interested, say, in a tunnel or a borehole at depth, and the rest of the medium is infinite, for a tunnel, maybe you can represent a tunnel in an infinite medium just like this, with individual nodes on the boundary of here. Which means that typically, if now you make the system of equations to represent this, you have a much fewer equations than you do otherwise. We know from our activities in looking at flow problems, we know that for each one of these nodes, we have 1 degree of freedom if we have heads. And so in this particular case, if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, I don't know, say 30 nodes, we'd have a matrix equation, Q equals KH, which has 30 terms in it, 30 equations to solve at one time. In this case, if this was the head of each node, we'd have 4, 5, we'd have 6, we'd have 7 equations. And so by using boundary element methods, we can sometimes use much smaller systems of equations, which are much more efficient to solve than if we use domain methods. Like anything, nothing comes for free. So the advantages of boundary elements are that they're very effective for linear problems, which have large, small surface to volume ratios. So in other words, something that's an infinite medium that doesn't have an external boundary, they work very well for that. But because you don't mesh nodes throughout the volume, you can't look very easily at systems where, for instance, the material properties are changing as a function of the pressure changes. So in other words, it's very easy for us to look at a permeability that might change as a function of pressure that we've looked at in our many slides in our class that say changes due to sorption and effective stress as a function of gas pressure. We can look at those changes in permeability in this system very easily. In this, we're almost always restricted to looking at the permeability which stays constant. Constant both in space, so it doesn't vary with location, and it doesn't vary with pressure either, pressure or time. And so like anything else, there are advantages and disadvantages of these systems. There is some material in your notes on boundary element methods, but we won't talk about it in this class. The material on those is actually available online if you want. No, okay, we won't do that either. Okay, so let's start talking about the solid mechanics part. We could derive the solid mechanics part in terms of a conservation equation, which is conservation of momentum. If we don't look at the dynamic case that includes inertia, then those equations become what are called the equilibrium equations. And so we could derive the behavior from the stress equilibrium equations. But actually, I think it's much easier to derive them from this principle of virtual work, which is equivalent to the equilibrium equations. And so that was the way that the finite element method was originally developed in this classic paper. We mentioned before that there were two competing groups who maybe co-founded it. One was Clough, who was at Berkeley at Boeing, working in the 1950s, and Aguirres, who was in Aachen in Germany, working on the same idea. And it was in the mid-1950s that these methods came out. And they revolve around this concept of virtual work. And virtual work really says something relatively straightforward. It says that if you take some body, I don't know what that body would be, I guess it's going to be really smoke.
destroying things here. If you take, oops, I don't took that one. I'll look for it later. So if you take a body and you compress it, then the forces that you apply on it and the deformation it goes through, if you take the product of those two, the force applied and the deformation it goes through, has to be contained within the body itself. And so the way it's contained within the body itself, forget that this is a bottle of water, is that this will deform, it'll strain, and there'll be a change in stress within this system as well. And so the energy, if you like, the work that you do on the outside of this, if it's conserved, has to be present as stored strain energy on the interior. And so the idea is that we can write this expression for conservation of virtual work, which says, here, I'll read it. An elastic body is in equilibrium. It's not going anywhere if for any set of virtual displacements, the virtual work of the external forces is equal to the virtual strain energy of the system. So that's saying exactly what that is. Take a body, you put some force, you have a force on it. If you make the displacements of that body some small displacement, then you multiply that force by that small displacement, and the product of force and displacement is work, virtual work. That work has to be present inside the system, and so if you measure the stresses that those forces apply to the system and the strains that now are made by that small displacement that you apply, the product of the internal strains that develop and the applied stress, and the it has to be equal to the displacement that you apply on the outside multiplied by the force that was already applied on that system. And so if you can quantify both of those two components, you can put those together to be able to explain the behavior of the system. And so that's what we're going to attempt to do. We can do that for a whole system, or we can take a portion of it out, which is this individual element. So we talked about the idea that we like to localize behavior down to a single element. And so in the same way that we can equate external virtual work and internal virtual work for this whole system, we can also do it for a single element M. And that element is going to look like something. It could look like a triangular element, doesn't have to. But now, as we said before, one of the reasons that we talked about flow first was it's simple because at each node there is a scalar property. It's either a flux or a pressure or a head that is defined behavior. And so both of those quantities, head or flux, are scalar quantities, but deformations and forces are very much vectoral quantities. A force has a direction and a magnitude. And so in 2 dimensions, each of these nodes would have a displacement in the x direction, displacement in the y direction, and also an equivalent force in the x direction and a force in the y direction. If we have 4 nodes on the element, there would be a total of 8 displacements, this one here, and 8 forces. And so where we developed our expressions before to describe behavior by the nodes, what we'll find out that we'll do now is that rather than describe it by the nodes, in which case the nodes have 2 degrees of freedom, 2 displacements and 2 force degrees of freedom, we'll tend to number these things actually by the degree of freedom. So instead of calling this node number 1 with ux and uy, node number 2 with ux and uy, we just sequentially and counterclockwise number the degrees of freedom. This 1, 2, 3, 4, 5, 6, etc. And that's just a convention, but it's a convention that works well for us. And so we said that if you put have an external force acting on this body and it goes through some displacement, then that force multiplied by the displacement you apply, the virtual displacement, is equal to the external virtual work. We can calculate that. Likewise, we can calculate the stress that force applies on the system, and the displacement that goes through will generate a strain, and we can calculate that and calculate the internal virtual work. So what we'll do is we'll attempt to calculate both of those. Well, what is the external work? The external work is just the force that's applied on the boundary plus a virtual displacement. So the force is already applied on the boundary, and what we're going to do is we're going to make it go through some small displacement.
And if we do that, we know that the work is equal to the magnitude of that existing force. We'll assume it doesn't change in going through this displacement. And so the work is just the product of these two. The force on the boundary multiplied through by the displacement that goes through. If we have on the boundary forces that are force 1 multiplied by its virtual displacement, force 2 multiplied by this, it's just the product of all of these components. And so the matrix relationship for this concept here is just going to be the product of the virtual displacements multiplied by forces. And if we want to define these virtual displacements, we'll define virtual displacements by an overbar in this particular case. So the work is going to be the virtual displacements u1 times f1 plus u2 times f2. In other words, this expression here. And if we write it out as a vector relationship, which we've had for the other components, it's just this displacement multiplied by the force vector, these two components. So that's our external virtual work that we apply in our bottle. So that's one part of this expression. We do it for a single element, then we have this defined. So the next part, what about the interior? Well, in the interior, we have a virtual strain. So these would be the strains that result from applying this displacement on the boundary. You apply this virtual displacement. The definition of a virtual displacement is a displacement that doesn't change the stresses. It's so small it doesn't change the stresses or forces acting on the system. So the stresses remain constant. The boundary goes through a displacement. If the boundary displaces and compresses the sample, there are strains that are developed in the sample. So these strains would be normal strains in the x direction, in the y direction, and in the shear direction. So shear strains are just the distortion of this body. You can think of a shear strain as taking a block that sits on a table, and you shear it with the boundary here, and it ends up looking like this, like shearing a pack of whoops. Ends up shearing like this. This angle alpha is equal to the shear strain that occurs. So this shear strain is basically that. And so likewise, kind of almost directly analogous to displacement times forces, strains times stresses. Strain is kind of a displacement that changes in space. A stress is a force that's applied over a certain area, so they're equivalent to each other. The strain energy is just the product of these. And so it's just equal to the product. I guess it's not written out. But the virtual work internal is just going to be epsilon transpose times sigma. This is a virtual strain. So we have that. And so if we want to be able to equate these, what we can do is we can look back at these requirements that we had. We had these four requirements. The equilibrium equation is satisfied if we have virtual work and external and interior work equivalent. The constitutive law, which I think was our third one, is Hooke's law that links strains to stresses. And continuity of displacements means that displacements are continuous. There's no jump in displacement as we move through our system. And that's accommodated by linking strains to nodal displacements through this A matrix. You remember before when we talked about flow problems, what was it? Rates of changes of head with location was equal to AH. Nodal values of heads, gradients of heads, nodal values of displacements, gradients of displacements. It'll be a different matrix, but it's the same idea. And then we apply boundary conditions. And so virtual internal work, well, I said it was at a point is equal to this. So this is the virtual work internal. But of course, it's not restricted to a single point. There's a strain here, there's a strain here, and here, and here, and here. And so if we want to accommodate all of those, we have to sum all of those up. It's different on the boundary for the forces, because the forces are only actually applied at point locations. So the product of force 1 times the displacement it goes through is a point quantity. And summing up those 8 point quantities gives us the total external virtual work. But the internal work is distributed throughout the volume of this. And so you can imagine, you can rationalize that the internal work is equal to the product of the strains times the stresses at every single point within the volume, which is just by definition the integral. So this is our definition of virtual work internal for the body. We have a stress here, which we can relate to Hooke's, let's see, what do we do? So I haven't done this. So this is Hooke's law. What happens if we, and this is, just as we said, strains or displacement gradients linked to nodal values in some operator. We don't know what the operator is yet, but we could, for instance, put this quantity in here. If we did that, we'd get the fact that stresses are equal to the elasticity matrix multiplied by AU. That's exactly what this is here. If we substitute in the value for the stresses into this, if we also substitute in the value for that we'll want to put this into here, which we have here, then we can do that. And so this is the transpose of this. So the transpose of this would be equal to the transpose of this, which is this. We'd make the case that since these are virtual strains, that these have to be virtual strains. And if we substitute all of these, we get the internal virtual work is equal to this. This is just by substitution. If we note that this transform is this, the product of two, the transpose of two matrices is individually the individual transpose of those two matrices, we can rewrite this term here as this. And if we do that, I suppose the integral should be out here rather than here. But because these displacements are applied only at nodes, they don't exist in the rest of the body at all. And so they're not distributed in the body. So we can take it so that the integral, instead of being written out here with this included in the integral, we can actually just take this outside the integral. And so if we do this, we have the internal virtual work, which is this whole thing. Likewise, we've taken this outside here. And because this is constant, we've kind of taken this outside here to get to this. And if we go back to look at what the definition of the external virtual work is, it's just the displacement, virtual displacement times the forces. If we equate these to each other, which is this here, we find out that we can get rid of this term and this term because they both exist in the same, on either side of the equation. And we have a relationship that links forces to displacements, real displacements, not virtual displacements, as a function of a stiffness matrix. And this stiffness matrix now is written for the individual element. And it's actually very similar to the stiffness matrix we had before. And so we can use that as our finite element statement. So the outcomes, I suppose, are that we basically have an expression that is AX equals B, a system of equations that we can solve. It's actually the same as Q is equal to KH, except for one slight difference. And the slight difference is that these displacement degrees of freedom are not necessarily one per node, but they may be in 2 dimensions, they'd be 2 per node. And in 3 dimensions, they'd be 3 per node, right? X, Y, and Z displacements. And so those are the things that we have to, the slight difference in this that we have to deal with. And so let's do a problem. We can do a problem very quickly after we get through the first part because you know exactly how to put these expressions together. And that is this. This is the relationship we're going to try and represent. These are what the individual elements would look like. This is our local element, which is our template. It has characteristics very similar to our flow element. It has a length, which is L. It has a cross-sectional area of the element, which is A. And it has in this case, nodal degrees of freedom, which are only one displacement degree of freedom in the x direction. We don't have horizontal displacements, or in the y direction, I guess, in this case. And we have nodes 1 and 2. So that's our template that we'll use to put on this. We take that template and we make a system which is more than one element. Global node 1, global node 2, global node 3, and those will comprise how we use these templates. But for now, all we have to think about is how we get this equations for this. We know that our stiffness relationship comprises these two matrices, which are the A and the D matrices. This is our constitutive relationship, which is Hooke's law, which says that stresses are related to strains through this. And so if this is the case, then Hooke's law would just be Young's modulus. If it can expand like a column in this particular case. And in this particular case, the strain displacement matrix would be that the strain du dx, du dy, I guess in this case, y is the direction, is equal to some operator multiplied by, what would it be, u1 and u2. These are the nodal displacements. So it's relatively straightforward. D matrix, as I guess we've alluded to, is just modulus, E, just from Hooke's law. This strain displacement matrix we can write as defined strain as just du y dy, which we can write merely as this if we take out the y value. And just as in any other element that we've dealt with, maybe we have done this before. If this is our element, and this is node 1, this is node 2, this is the direction y along the length of it, and this is displacement uy, then we're going to choose the simplest displacement regime we can. This is u1 to this point here, this is u2. And so the question is, what is the equation of that? Well, we know exactly what it is, right? Because we've done it before. Yes. Okay, let me change that around. So change this, just then it keeps the equations the same. This is u1, 2. Yeah, right. It is. It's done here, right? Just it doesn't matter what the convention is. It works either way. It's just in terms of the way this is written is that. So the equation for this curve now is displacement y at any location is equal to this. So at y equals 0, this is 0. This term drops out. The displacement at y equals 0 is u2, hence this. And the displacement at y equals L, so this is length L. So y equals L would be this point, so this would be 1, u2 minus u2 is 0, and you're left with 1. So it gives us the requirements that it recovers the displacements at the right locations, which is basically what this is saying here. These two statements. So what we could do is we could take this relationship and throw it in here. We can take the derivative of this. So if we take the derivative of this, what do we end up with? Only this term will survive. The derivative of y with respect to y is 1, so this becomes u1 minus u2 over L, which is this. And if we write this expression out by separating out the displacements in terms of just a matrix, then this term here, which is this whole term here is exactly the same as this, then this just becomes the A vector. And so once we have A, which is this, and once we have D, which is this, we have enough to be able to put together this matrix relationship here. And if we do that, then we can just substitute those components in. This becomes 1 over L 1 minus 1. This becomes the transpose of that, which is 1 over L 1 minus 1. This becomes modulus, which is just what's written out here. And if you multiply those together, not surprisingly, this times this goes here. This times this goes here, etc. And the other terms you have that come out of it, it ends up with, after you do the integration, it looks identical to what we had before. So this is just the same. All that is different is that now this is modulus instead of hydraulic conductivity. And that's the only difference. And this is a stiffness matrix instead of a conductance matrix. We should caution ourselves, I guess, the fact that in this particular case, this has been 1 degree of freedom. And so it's a one-dimensional problem still. So the same as the number of nodes, we have 1 parameter per node. That won't always be the case, and it sometimes gets a bit more complicated. For instance, when we have 2 degrees of freedom per node. And but for this particular case, it ends up being identical to the equation we had before. If we want to solve this problem then we have to supply some boundary conditions. Let's fix the base so the base can't move. Let's apply a force at the top. And then solve it for the displacement that results from that force. So I'm not sure what those magnitudes are, but it means that to be able to put this element together, then we have element number 1 and element number 2. This is element number 1. This is element number 2. As it goes into the global elements. And we have forces and displacement. So it's entirely analogous. If we're going to apply this force here, which is 5, then by definition, we said that forces are vectoral quantities. So this is the force at node 1, but it's in the negative y direction. So this is minus 5. And we're going to fix this, so the displacement at node 3 is equal to 0. So those are our known conditions. Our unknown conditions are, what is this force here? What is this displacement here? And we know that the internal forces, just like the internal fluxes, F2 will be equal to 0. Because the force from one has to be reacted against by the force from the other. And so we can deal with that. And so once we have this matrix, the parts that we know are that this is minus 5. We know that this is 0. And we can figure out how to be able to solve this system. Remember before that when we dealt with the flow problem, we had a head at node 1 and a head at node 3, and those are defined. And so the analog for this would be that the displacement at node 3 and the displacement at node 1 are both defined, and then we only have a single central equation to solve, and it becomes very easy. In this particular case, we don't know what this is here, and we don't know either U1 or U2. So it's going to be a little bit different from the case we had before. So yeah, so this is the resulting system of equations that we get. Whoops. Oh, good. It's gone crazy. Okay. Right, so what are we going to do? Well, how do we solve that system? So we're going to want to solve for displacement 1 and displacement 2. We have enough to be able to do that. And so if I keep this open on both cases, what do we want to do? Well, what we could do is we could use this term here, which we know, and therefore all the terms in this column, to be able to in turn multiply this value by this and take it off to the left-hand side. So 0 multiplied by 0 is this term here. 0 multiplied by minus 2 is this term here. And 0 multiplied by 2, which goes on here, is this term here. So that's all we've done here. We've got rid of this term and this column. So we have now 2 columns that we know. We only have 2 unknowns. So actually we don't care about this bottom part. So we'll solve everything above the dotted line. And if we want to solve the problem, we can invert this. How do we invert this matrix? So the inverse of this matrix, well, I won't do it. If you wanted to invert this, you just do what? You switch these properties, you make these 2 negative, and you divide through by 1 times 3 minus 1 times minus 1. It's just, so this is our K matrix. If you wanted to get K minus 1, it would be equal to what? It would be 3, 1. Switch these terms. It would be plus 1, and it would be divided by 1 times 3 minus 1 times minus 1. So I'm not going to do the calculation, but that's how we would get the inverse if we wanted to use it. But if we solve it, let's say that we have solved it, we get the values of u1 and u2 are those. And so now we know exactly what these values are. We only have 2 unknowns. We know everything on the left-hand side, right? We know everything in these 2 values. We know everything in the matrix, and so we can solve for these 2 values. Let's say we've done that, and we have them. And then, now what? Well, what we can do is we can resubstitute them into this. So we know that u1 is equal to minus 15 over 2. We know that u2 is equal to 5 over 2, minus 5 over 2. And we know that this is 0. So we know everything in this vector. So multiplying them by this matrix allows us to be able to confirm that f2 is indeed 0. Well, we assume that this is 0. And that we could now calculate what f3 is, which is what this reaction. And if we do that, we'd find out that, well, yeah, I won't do it. If you go through it, you'll find out that the value of f3 is equal to plus 5. And so we can work out whether that makes sense. Does it make sense? So if we look at our geometry, we draw our geometry. These 2 elements. We have a force down here which is equal to 5 going downwards. We have a force here which is equal to y pointing upwards. And so the magnitude of F3, which is our reaction, is plus 5 in this direction. And so that makes perfect sense, is that you have a reaction equal and opposite to the other force that's being applied. And the other thing I guess we should work out, I guess I didn't say in this case, is that we're going to we have chosen a magnitude for this stiffness of these 2 systems where this modulus is different. And it's different because in this particular case, for the bottom element, it must be, oh, that isn't, it's the same. No, I guess it is different. So we've chosen a modulus for this bottom element here, which is twice as much. So in other words, E2 is equal to 2 times E1. So it's not homogeneous. Hence this value here, because these are just linked by this constant. Everything else is the same. And so the bottom element is twice as stiff as the top one. So E2 is equal to 2 times E1. And this is E1. And so what's the displacement? If we plotted displacements of these versus depth, then the displacement at the top one is equal to minus 15 over 2. At the bottom one is, bless you, minus 5 over 2. And so it actually looks like a straight line here, but it's not. That's better. Yeah. And so does that make sense? Well, it makes sense if you look at the difference between this. This displacement that occurs here is going to be the difference between these, which is minus 10 over 2. And so what it's saying is that the deformation that occurs in this top component here is actually twice as much, 10 versus 5, that occurs here. And that's exactly what you'd expect, right? If this is much stiffer by a factor of 2, then it would deform less. And so we could calculate exactly what the amount should be, and you could do just by using Hooke's law. The magnitude of this would actually be the right magnitude. Of course, there's a huge magnitude, right? I mean, the modulus that we're using shouldn't be a modulus of E is equal to 1, A is equal to 1, L is equal to 1, because modulus is typically a very, very small number. This, of course, means that the displacement that we get is actually larger than the length of the element, which is only 1. So that's nonsense, of course, right? It's turned itself inside out. But if E was actually a normal magnitude for a rock, which would be 10 gigapascals, then this would just be 5 times 10 to the minus 10 MPa. And so it gives strange results. It's easy not to work with that full number here, just because it makes life a bit easier. So that's it. And so it's really no different from dealing with the flow problems. We can rationalize the results in the same way as we can rationalize the flow problems, and that's fine. If we want to look at triangular elements, then that follows also directly on from our other behavior. But now, I guess what's different is we don't have the luxury that individual elements, or individual nodes rather, we don't have a single degree of freedom. We have 2 degrees of freedom. And so we have to accommodate that in some appropriate way. And so maybe, I think we have time to do this before we finish this section. So let's just go through it and see exactly what this would look like. Okay. So this is the geometry of our element. It has a right angle in here, but it doesn't have to. It could be anything. It's composed of 3 nodes. It has an area. It has an area modulus attached to it, and a Poisson ratio. It has nodal coordinates of xi, yi at node I, at node j, and node k in this particular case. We have used k because we're not using permeability now. It has displacements at the nodes in the x and the y direction, and we just number those sequentially 1, 2, 3, 4, 5, and 6. And actually, as we know, we'd always have complementary magnitudes of forces at each of these points as well. So this would be F1, this would be F2, etc. We always number our element counterclockwise for the reasons that we talked about before. It's only because when you calculate the determinant which you use to get the area, you end up with a positive area. If you numbered it clockwise rather, you'd get a negative area. So it'd be easy to deal with that, but it's just convention that we do it counterclockwise. And what else? We always define positive values of displacements and forces in the positive values of the coordinate system. So I guess this would be a right-handed coordinate system. This would be x direction, y direction, and z direction would be out of the board at you. It's not particularly important, but that's the standard convention for this. And you'll remember when we did this for the flow element, what we did was we defined a shape function. And what we drew this little picture. That was the fact that we'd have an element that sits down here, and that we'd have a height of head at node 1, head at node 2, head at node 3. And if we wanted to link those up, we could do it with a single plane that would go through those. That was our kind of shape function. If we wanted to actually decompose this plane, actually we could make a shape function for h1 that would look like this, going down to this point and in the background like this, and then put them together. But let's not do that because it would just maybe confuse us. So what we could do is we could write a displacement in the x direction at node 1, a displacement at the x direction at node 2, which is u3, and a displacement in the x direction at node 3, which is u5, and think of those as these heights, right? And if we do that, then we can also write the equation of a plane that would go through the magnitudes of these three displacements. Even those three displacements aren't a height of a head, they're actually just a magnitude of a property. We could think about it going through those elevations of those points if the height was representing the displacement. So in the x direction, we could define this plane that is a constant, and a constant, each of which we don't know, but modulated by the x coordinates of any point within the element. So if we know what a, b, and c are, and we know what the x coordinates are within the element, that would tell us exactly what the x displacement was at any point that we choose within the element. That's the definition of it. And that's useful because ultimately we'd like to be able to define strains in our system, which are gradients of displacement in the x direction as a function of x. And so if we want to get the strain, we know it's equal to the derivative of ux. This is ux. If you differentiate this with respect to x, you lose this term, and all you're left with is b. If strain in the y direction is defined as displacement in the y direction and how it changes with y, this displacement gradient, then we can take a similar expression where instead of doing the u1, u3, u5, it would be u2, u4, and u6, again for a different plane. It would be defined in terms of different values of these variables, and the derivative of this with respect to y is going to be this term here, f. And if, we haven't really talked about this, but by definition, the shear strain is the off-diagonal terms, dux instead of dx, it's dy, and duy instead of dy, it's dx. Then the derivative of dux with dy would be this equation and c. The derivative of duy dx is going to be this equation and this term here, which is e. So the point is, if we want to be able to define our strain displacement matrix, which is this, the components of strain that we have are strains in the x direction, strains in the y direction, and shear strains gamma xy. Which are these? Then immediately we know exactly what these are because these are these. And so these are our nodal displacements. And so what we'd like to be able to do is figure out exactly what the A matrix is by knowing exactly what these are. And hopefully these values in some way, the B's and the F's and the C's and the E's, will relate in some way to the nodal displacements. So that's going to be our hope. So that's basically what we're trying to do. So what we'll do is that we now need to figure out exactly what, well, we need to know B and C for sure. We need to know F and E because those occur within these relationships. We don't care about A and D, but we need to get them anyway, but we don't really care about them because we won't actually use them. And so how do we figure out exactly what these coefficients are? Easiest way is to make the values of these displacements at nodes 1, 2, and 3 equal to these magnitudes and write the equation in terms of one equation at node 1, one equation at node 2, and one equation at node 3. So in other words, we'll take this and we'll write it 3 times. We'll write it at node 1, where we know, or sorry, for degree of freedom 1 at node 1. So this is ux at node 1. And we know at node 1 the coordinates are xi and yi. We can write it in terms of displacement degree of freedom in the x direction at node 2, which is u3. These will be the coordinates of that node. And likewise, the displacement in the x direction at node 3, which is u5. So these are the degrees of freedom of our system. We can write this again as this, as a matrix equation. Or we'd really like to have it define A, B, and C as a function of the other terms here. So we can write it in this way that it's defined here, but really we want to solve it in terms of this. So we just invert this matrix now by taking the inverse of it. We've already got the solution, so let's not do that again. And it now defines the values of these terms. We know that of these terms, we're actually only going to want the values for B and C, and ultimately F and E as well, but for this one we just need B and C. And so we're only ultimately going to need these. And so actually the top part of this we can just throw away. We don't care about it. And so we're going to need just the lower part of this. And so I think in this we used the standard notation. We used A11 and A12, etc. This is just beta, but it's exactly the same expression that we had when we looked at flow elements. And so this term here is this term here. This term here is this term here, etc. Okay? So the bottom line is we have the ability to get B and C. We want to be able to get B and C because B and C is going to be the normal strain in the x direction, and it's going to be a part of the shear strain in the xy direction. And these values of BC are a function of only the coordinates of the nodes and also the magnitudes of the displacements. So what we can do, I don't think we need to do that. So we have this equation, and so we'll stop here and we'll come back to it. We have these other 2 terms we'd like to figure out. So we want to know exactly what F is, and we like to know what E is as well. They occur in the equation for Y. And so now we can do exactly the same for Y. We can take this expression, we can write it once at node 1, where we know the coordinates and we know the displacement in the Y would be U2. We can write it once at node 2, where the displacement in the Y direction would be U4. And we can write it at node 3, where the displacement in the Y direction would be U6, and we know the coordinates of those points. So just as we did it here for this earlier expression, we just repeat. I'm not sure whether I write it out in longhand or not. Yeah, I guess I do. And we get an analogous result, which is actually identical to this. It's exactly the same as this expression here. But instead of this, this, and this, and this, this, and this, then it's just going to be U2, U4, and U6. And this is going to be E, F, and G. Because we're basically just, instead of doing it for these 3 ones, this equation written out here, we're doing it for this equation here. So it'll be U2 multiplied by D plus EX plus FY, etc. And so we'll end up with another matrix equation, and we'll end up with values of these nodes. And actually this matrix equation will have exactly the same terms in it as before. These terms here will be identical to before. All that's different is they're operating on different magnitudes of the displacements at those components and give different values of these terms. Okay? So we have equation 15, which looks like this. We have equation 11, which looks like this. And what we want to do is we want to make a relationship which describes this behavior here as a function of these. And so the other thing that we also know is that, I'm running out of space to write it, is that we could write out here the fact that epsilon x, epsilon y, gamma xy. We could also write out that this is equal to b, this is equal to f, and this is equal to c plus e. So these are just writing out this expression. I guess all we're doing is writing this out as a function of this. That's all I've done. And so now, if we figure out exactly what b is, and we like to write this now out in longhand as u1 all the way through to u6. So the next step is to be able to realize that we know exactly what this is now in terms of this beta matrix and the nodal degrees of freedom. And so what we'd like to be able to do is write out each of these terms in turn and relate it to the displacements at the nodes. And if we are able to write out b as a function of displacement to nodes, then the components that go into the matrix that links those is going to be, by definition, the A matrix. And so that's the final step. So remember the fact that we have this matrix here that links, that we're going to be interested in B and C from. We have this matrix here, which we're going to be interested in E and F from, because each of these components contribute to this. So B and C, E and F. And now all we need to do is to populate this. So this is the same as, what was it? This was B, this was C, this was E plus F, I think. Let me check, just in case it's not. No, it's not. This is F and this is C. And so now, if we know what B is, let's look at it. B is equal to this constant, this times this, plus this times this, plus this times this. And so this is x displacements at nodes 1, 2, and 3. So in other words, it would be B21 times this term, B22 times this term, and B23 times this term. The other term, F, which is a bit easier to do because it's right here, F is equal to this term here multiplied by U2. This term, so in other words, this is by U2. This term here times U4, so it's by U4, so it must go in 1, 2, 3, the fourth location, which is here. And this final term operates on U6, which is this here and this here. And then we just take the remaining components for this. So this is E. E, how am I going to do this? Can I do triangles? Would operate on U2. This would be 2-1, that is right. This one here operates on U4, it should be this. And this one here operates on this. And then the remaining one is just recovered from this expression for C. So I won't do that, but that's it. And so it gets a bit more complicated because now you realize that we're dealing with these 2 degrees of freedom per each node. But if we want to be able to put finally the stiffness matrix together, then what we need out of this are magnitudes of the A matrix, which we now have. By definition, this is our A matrix. A bit complicated, but not terrible. And we need our D matrix. And we haven't said anything about the D matrix yet, but take it on trust that this is what it looks like. This is what Hooke's law looks like when we have plane strain. And again, it's 3 by 3. And so we have this. And if we have each of those, we have enough to be able to put together the I need to do that. We have enough to be able to put together the relationships for that. So that's it. The trick, I suppose, in this is that we need to be able to now get this matrix which defines these behaviors. But these, what are the components of this? I guess the other thing I suppose we can do, and we haven't noted, it's not noted here, but what do we know about this A matrix? This is 1 over the 2 times the area of the triangle. So for any particular element, that would be a single constant value. The magnitudes of these terms, beta 2,1 and 2,2 and 2,3, we have talked about already as well. And so in other words, this would be beta 2,1, this would be beta 2,2 and 2,3. They're just magnitudes of the differences between the coordinates of the node. So these obviously for a single element are constant within the element. And so just as before, when we look at this matrix here, we could actually rewrite this matrix for the stiffness, which is equal to A transpose dA dV. Since the A matrix is constant, it doesn't vary with location of the element. The D matrix is constant, then we can also write this as A transpose dA times the integral dV. And this integral dV is just the area of the triangle times the thickness of the triangle, right? If it's a triangle element. And so it's very simple to be able to do because we notice that the magnitude of this matrix, we can take all of these terms outside the integration. And so we don't have to worry about that. D is constant and A is constant as well. So that's useful. So it makes it easy for us to be able to assemble this. And the only trick is that in assembling this A matrix is a bit more complicated because now instead of being 3 rows and 3 columns, now it's 3 rows and 6 columns. And it's 3 rows and 6 columns because we have 6 degrees of freedom within the element rather than just 3 magnitudes of heads at each of the nodes. And so it gets a bit more complicated than that, but otherwise we don't have to worry about it. So maybe we'll take a break there, and what we'll plan to do is to, this afternoon, look at what these matrices look like, try and reaffirm what we understand about why the constitutive matrices look like this, and solve a problem maybe with EGEFEM. So that will take up one of the sessions this afternoon. And then the remainder we can look at couplings between flow problems only, such as dual porosity and dual permeability models. And then finally we'll talk about coupling between mechanics and flow. Now at least we have the beginning of the mechanics part taken care of as well. So that's our plan.